We are taught early on that solar systems are built on order. A star ignites, and the leftover dust and gas settle into a flat, spinning disk, eventually clumping together to form planets that trace calm, predictable circles. You can see this stability looking at our own cosmic neighborhood. Jupiter, for instance, has sat in its reliable, nearly perfectly circular orbit for billions of years. Because we grew up in this quiet corner of space, we naturally assumed the rest of the universe operated under the same strict, polite physical laws. But when we launched advanced observatories like the Hubble Space Telescope into orbit, that neat rulebook was thrown out. Staring deep into the void, we found a chaotic laboratory of extremes. We found places where our gravitational math breaks down, and where intense radiation warps matter into unrecognizable states. We are cataloging the specific anomalies that deviate from standard physical laws, investigating why these worlds exist where they shouldn't. Standard models state planets should travel smoothly around their star's equator, orbiting in the exact direction the star spins. Then we found GJ436b. Instead of circling the equator, its path snaps into a harsh vertical loop, traveling directly over the star's poles. Because it follows this punishing path, the host star constantly blasts the planet with intense radiation. The atmosphere is violently cooking off, creating a trailing hydrogen cloud over 8 million miles long that makes the planet look more like a colossal comet. WASP-17b takes this rebellion a step further. It has a retrograde orbit, meaning it travels in the complete opposite direction of its star's rotation, a trajectory that suggests a violent gravitational collision through it completely backward. And then there is HD 80606b. For about 100 days, this world drifts through freezing, pitch-black space on an incredibly stretched-out path. Then it begins a terrifying dive. Over a span of just 20 hours, it plummets straight towards its sun. This rapid approach suddenly flash-fries the surface. In only 6 hours, the temperature on the day side skyrockets to over 2,000 degrees. The atmosphere simply cannot handle this sudden injection of extreme heat, violently erupting into 11,000-mile-per-hour shockwave storms. These aren't the products of a gentle, swirling dust disk. Near misses, planetary collisions, and extreme gravitational wrestling matches are what actually forge these nightmare trajectories. This chart maps planets by mass and proximity to their star. Notice this empty zone, the Neptunian desert. In theory, extreme radiation should boil a gas giant's atmosphere entirely. Yet LTT 9779b sits perfectly inside this forbidden zone, completely intact. It survives because the brutal heat cooks its dense atmosphere into vaporized metals. These heavy elements condense into massive clouds of titanium and glass, acting like a giant mirror in space that bounces 73% of the incoming starlight right back into the void. This stands in stark contrast to TRES 2b. This gas giant absorbs over 99% of the light, making it darker than coal. It's so hot that reflective clouds like ammonia simply cannot condense, leaving a pitch-black world that emits only a faint, dim red glow like an electric stove coil. The intense heat drives kinetic extremes. On WASP-127b, the 2,000-degree atmosphere generates supersonic winds that tear around the planet's equator at 20,500 miles per hour, fast enough to cross the Earth in minutes. A host star's relentless energy doesn't always destroy a gas giant. Instead, it forces the atmosphere to adopt bizarre survival mechanics, mutating into metallic mirrors or absorbing light into pure darkness. We usually assume that a planet's lifespan is tied directly to its star. When an aging star runs out of fuel and expands, it consumes its inner planets, completely vaporizing them in a wall of plasma. About 18 million years ago, a planet called KOI 55 was swallowed whole as its sun expanded. It plunged deep inside the star's burning layers. Most worlds would instantly dissolve, but this one survived. The star stripped away all of its gas, leaving only a burnt, rocky core behind. Even after millions of years, the remains of KOI 55 are still scorched at 12,000 degrees Fahrenheit. Other worlds are born from the ashes of dead stars. The very first exoplanets we ever found orbit a pulsar named Lich, the crushed, rapidly spinning remnant of a dead star. These zombie planets formed out of the debris left behind when two white dwarfs crashed into each other. Standing on one of these rocky tombs, you would be continuously bathed in sterilizing radiation. Looking up, the sky would flash like a violent strobe light 160 times a second as the dead star spins, rapidly firing beams of energy. A solar system's story doesn't cleanly end when the primary star dying. The planets left behind are simply forced into a tortured, perpetual undead state. Human perception has its limits. Even our most advanced telescopes are occasionally fooled by ghost worlds that appear to vanish back into the darkness. In 2008, astronomers celebrated the discovery of Fomalhaut b. It was one of the first exoplanets caught directly on camera, but over the next few years, the tiny dot of light slowly stopped glowing, drifting off its path until it completely vanished into the darkness. Fomalhaut b was never a planet at all. That bright dot we photographed was actually a massive, expanding debris cloud left over from two icy asteroids smashing into each other. We didn't capture a planet, we captured the aftermath of a cosmic crash. A similar illusion occurred with HD 188753AB, reported as the first planet found in a tight triple star system where 3 suns would light up the sky. 2 years after its discovery, a different team using highly precise instruments looked for it again and found absolutely nothing. The planet simply vanished, leaving an unsolved mystery. To pierce through these illusions, we have to rely on next-generation observatories. Instruments like the James Webb Space Telescope are currently cutting through the dust and glare, parsing out the exact chemical signatures of these distant environments. The discovery of these worlds provides the necessary data to refine our models of planetary formation. They demonstrate that the orderly patterns found in our own system are merely one possibility in a much more violent and diverse universe.